All right, everybody, so we will start the session for the afternoon, and that's thermal, so heater design guide on heater elements. Here we're talking about particularly electric heater elements, which are very common in many different applications of the Global Village construction set. Right now we've got the experience with things like the extruders for making 3D printing filament. We've got experience with making our own heat beds for the 3D printer. Advantage being they're scalable, modular, low cost. We can make them as large or small as we need to. And we'll talk about here how we can leverage the power of nichrome wire, which is resistance wire that does not oxidize at high temperatures and gets you to temperatures up to like 1400 C with nichrome or canthal wire, which is good enough to melting iron, such as cast iron or ductile iron, which are actually quite usable. So let's start. Just overview of the different applications. You've got heat beds for printers. You've got heated enclosures. You've got extruder heater elements for 3D printers. 3D printer filament makers. Those are some applications that come offhand into my mind. Then we could be talking about other electric heater elements, applications to other different devices. And is everybody good on the remote? Can you guys all hear me? I will say yes unless you say otherwise. Other applications of heater elements, things like heat guns. Okay. Things like washing machine dryers.
You're a really good dude.
That's thermal power, that's electricity.
Hey guys, can you keep it down, please?
Thank you. Okay, there's people here. Heaters, okay, so electric clothes dryers. Now, of course, going from electricity to heat is not super efficient, but it is convenient to do. Like, you don't want to be heating your house on electric because that's a waste of high-grade electrical power. But in the case of the low-cost photovoltaic panel access, using electric heating for various things is okay if you have excess electrical power. Like, for example, if you've got an excess PV array, it perhaps even makes sense to do electric on-demand water heaters, which stay on just for the time of the use, so you don't have to be heating a big water tank. So there are various applications throughout that are relevant for understanding nichrome heater elements. So let's talk about nichrome heater elements. Design considerations. So if you're working with nichrome, the first thing you have to do is understand how much power and how much heat you're going to use by a nichrome element, so without burning it out, without getting over temperature, or without not being warm enough. So you go straight to a nichrome calculator. Online you can find nichrome calculators, like for example the one I linked to. Let me share the screen. In the design guide, that's the first link. Start with nichrome calculations. How long will your wire have to be? What gauge will it have to be? And how much power will it use? Because if you maybe use a very fat nichrome wire, plug it into the wall, it might pop your breaker because it's drawing too much current. So you have to understand some basics here. So this particular calculator, you can Google nichrome wire calculator, but you can do that just offhand. You can say, okay, I've got so much length, so much gauge, and the desired temperature that you want. It will tell you what voltage is required, what its resistance, voltage, basically voltage and power requirements for that wire. So say you've got, like in our example, 13 feet, so let's do feet here, of 26 gauge nichrome wire, and you want it to get to like 1200, like 900 C maybe. Calculate. And it tells you the power. It says you're going to need 100 volts for that. It'll draw 3 amps of current, and it will draw about 300 watts to do that. If you want it to get up to 1000, you'll have a little more, say 1300, 1200. let's say 1100. So you kind of have to play with this to understand, like, basically this is saying to us if we have 13 feet of 26 gauge wire, it will get to 1100 Fahrenheit at a voltage of 121 volts. It will draw about 425 watts, and this is actually the use case of what we're doing in the 3D printer. Now you might say 1100, wow, that's a little high for a 3D printer. Well, yes it is, but we've got a controller that you turn it on and it draws 400 watts of power about, and it heats up quite rapidly. But you can play with this to get different gauges, different lengths of nichrome wire, and it'll tell you what the required power and voltage is for that given wire. In the case of nichrome wire, the big point to consider is how are you going to insulate that? Because nichrome wire is actually carrying the live electricity. It's a nickel chromium. It's made of nickel, forget which is which, the 20%. So nickel chromium, I think the bigger value, like 60% of it is nickel, and then chromium is like 40 or something like that. But nichrome refers to the two components of the wire, which are nickel and chromium, the combination of both of which mean that they are conductive, they pass current, and also they do not burn out or oxidize at very high temperatures, because they can go up to 1400 Celsius, that is. That's a lot. So typically, they start glowing white hot or red hot. A normal steel wire would just burn out over time. It would rust and oxidize and go away. The special property of nickel and chromium is that they do not oxidize at the high temperatures. But you still have to insulate them. So in the case of our 3D printed bed, we insulate them and we control them through the Arduino controller with a solid state relay power switch. So let's take a look at what that actually looks like for the case that we're using right now and building right now. And before we go there, let me just link to when you have these high temperature devices, you need to have another very important component is your temperature sensor, which would be a thermocouple or a thermistor. You need one of these so that you know what temperature you're at. So with that said, let's go to the building your own heater what does this look like? But before I go there, in the design phase, I'd like to point out that in FreeCAD has recently added the thermal design workbench, so it looks like this. What this says is that you can draw various shapes within FreeCAD, and this is within the finite element analysis workbench, and you can actually simulate the thermal spread when you apply a heat load to a piece of geometrical object. How will it heat up over time? You can do that within FreeCAD, so you can take a look at that and start playing with that to get a handle of that, and then you get to the build. So let's look at the 3D printer heater bed. On the wiki it's under 120 volt heat bed, and I've got some new pictures from the recent build right now. So here it is. You've got nichrome wire. That's what you see there, the white stuff, that's the white insulation. That's 1/4 inch fiberglass sleeving material, and we send the thin nichrome wire through that and basically wrap it in a pancake. In this design here, what we were doing simply is taking a length of nichrome wire and feeding that through the sleeve, and that's what we did, and then we connected that to the copper wire. Now there's a special note about connections. You do not want to solder your connections to nichrome wire because the nichrome wire can get quite hot. Solder melts at, say, 300 Celsius. Here you have the potential to go up to 1400 Celsius. So you do not want to rely on a solder connection for connecting your nichrome heater wire to copper wiring from the power grid, or whatever you're using for power. What you want to do in that case is using crimp connectors, which are just simple sleeves, little sleeve bushings that you can crimp using a crimping tool. So if you go to the 120 volt heat bed in the bill of materials, what do those things look like? So I have an extensive page for sourcing of all the materials. If you want to build yourself an open source 3D printed heat bed, you have choices of aluminum, steel, tile, The advantage of tile is that it's non-conductive, so if you have any kind of a electricity short, tile is insulating, so you won't shock anybody. So there's a bunch of tile options. That's good. The disadvantage being that they'll take a bit of time to heat up. You can have silicone rubber sheets. The way you attach, what we do is we attach polyetheramide printing surface to that. I'll talk more about that. You got links to the nichrome wire. Sleeving. Sleeving is 20 cents per foot from McMaster Carr. If you go to that, this is the actual sleeving that we're using. Fiberglass, high temperature sleeving. We're using 1/4 inch diameter. And that's what it is. A 100-foot piece costs you $31. So it's actually looks like this went up since I ordered about a month ago by about 50% in the war with China. So you can see those links on the wiki. People also use carbon fiber, believe it or not, for heating wire, and you can see that used more for lower temperature applications. So that's because carbon fiber, I guess it's conductive. Yes, it is. Here's an example of a nichrome heater used for like a chemistry bulb heater, kind of for flasks. Here's other examples. I want to see a link to the, this is 120 volt heat bed. I want to see a link to, I wanted to show you the crimp connectors. I'll go to Amazon. It's a quick way to pick things up here. So nichrome. For nichrome, you want to use sleeves that you use to crimp with, and they look like.
Good.
Simply because you cannot solder, you want to be very careful about what you're doing there. So here's the supply of these metal uninsulated wire ferrules. That's what they're called, cable crimps. So you have to crimp that on the wire ends to connect the copper to the nichrome, because otherwise you would be melting the solder and you'd have a dangerous short circuit. So this is the way to do it. And to show you the actual build, so this is fresh, hot off the press. This we were working on yesterday. So what you're seeing here, look at this beauty here. So what we have here is we're actually loading these insulated wires into the heat bed, and what we're doing right now is using a 120 volt insulated heat bed to run this, to do this. Let me make sure I'm recording. Yes, we are. This is from yesterday. We're doing a batch of these, and we're basically coiling it around on fiberglass. This is not fiberglass, this is actually rock wool insulation. It takes a higher temperature than fiberglass. So the heat bed is actually essentially a steel 1/16 inch or 16 gauge steel that we make the bed from. We wrap the coil around, and then you connect it to high temperature wire. This is 200 Celsius copper wire, rated for such applications where it can take a little bit of temperature, as opposed to plastic coating, which may be like rated, say, for like 80 Celsius. And then to show, that's the heated bed on the bottom. That's a steel surface. We're attaching it through 2 bolts, and I'm using a 3rd bolt to clamp this thing down, to clamp the top surface down. This is the finished beauty. So what you see here is a 1/8 inch top plate. It has a metal elongated nut welded to the bottom of that, and we send a bolt through the bed in order to pull this top surface down. Matthew?
Was the top one an 1/8 inch, or was it the bottom one an 1/8 inch?
The top here is 1/8 inch, and we wanted that to be 1/8 on top because we wanted it to be heavier and to bend less. The bottom, but we did want to make this pretty solid. So this is 16 gauge. This is not sheet steel. The last version we built was sheet steel, and we found that it wobbles too much. We wanted to make it super solid for high-speed printing, making your entire printer industrial grade. What we have here also is the PEI, the polyethermide surface, which has a working temperature, long-term working temperature of up to 177 degrees Celsius. So our current heat bed for the 3D printer is rated for continuous operation at 177 Celsius. That means some high temperature plastics you can also do on this. We attach the polyethermide PEI shiny surface to the metal using double-sided 3M tape. It's also in the bill of materials. And the property of PEI, this advanced plastic, is that when you heat the bed up, the concept for heating is when you heat the bed, things stick to it. And polyethermide is such that it sticks very hard when hot and pops right off when cold. So it's a very efficient way for part removal. You can think of having a bumper of some sort bump parts off when a part's cool, because they are really easy to get off. Especially if you even, you can add a mechanism where you cool the bed. And that way they come right off, they'll pop off. At room temperature you can get them off, get the parts off without much force. When you cool it further, yeah, they're completely off. More details of how we were doing. Here we were cutting, there you see these surfaces here are the double-sided 3M tape. So we put that on the steel surface first. We peel one side, roll it on. The way to apply it, you don't peel the entire side, you peel a little bit, and you kind of roll it on while taking off peeling off the tape of one side, so you don't get bubbles in there or get it on straight. Because once you get it on, you pretty much can't take it off. So we cut the sheets to size, including the PEI to size from stock. Then we attach it, and then we've got the ready-made bed. But the bed does look pretty sharp. It's very solid. This is pretty good. Then I got the Pan Industrial Revolution from our fellows here. This is some good books to read. Okay. So let's go back to other things. Types of heaters, bed, furnace, other. Other applications that we can use with the use of nichrome heaters is simple kiln that you can melt metal. Like for example, if you want to do a low-cost nichrome heated furnace, there's a lot of plans online where you can see how these are made.
Hey guys, today I'm going to be showing
furnaces
you
that
how
use
to make
nichrome wire for heating and melting aluminum. You can't do steel, but you can do iron, like ductile iron or cast iron. That's doable, but in that case you would have to use Kanthal wire. So here's an example of a video where you have a ready-made homemade design using fire brick. Fire brick is not exactly that cheap. You can also use refractory material that you can cast your insulating material and then put the nichrome wire inside of it. The advantage of using a ceramic insulation is that you can put the nichrome wire right into it. It's insulating. So if you made some structures to hang your wire in there, you can do that. And these are actual tests. This is just something I picked off the internet just to show you what can happen. But you can do things like melting aluminum right in there, and this is using electricity converted into heat, and that does work. So you buy yourself a crucible off the shelf. He also did some experiments where you're using arc melting. But the relevance to the Global Village construction set and 3D printing in particular is that using a simple surface furnace like this, we can be doing PLA, lost PLA casting. So you can 3D print an object, cast plaster of Paris around it, and burn that shape out, or just use special filament. They also have special filament where you can 3D print the object, put the cast around it, and you can pour directly into it and it burns out. There's some specialized filaments that you can use to do exactly that. So this becomes a method where you can convert your 3D prints to full metal objects in aluminum at least. And if you had higher temperatures, if you talk about steel, you need to go to other refractory materials beyond plaster of Paris. So that gets to a little more complication that could benefit from a lot of open sourcing, because you can't readily find good blueprints online. You can find plenty of material about aluminum, much less about steel, and I haven't seen anything with lost PLA or like 3D printed. Yeah, I haven't really seen it. We can, yeah, there's more, but could definitely benefit from some open sourcing of the whole production engineering of that to make it replicable. Once again, video online is nice, but you need some more complete bills of materials and exact process information where you can repeat that without having to go through all the experimentation. So it's another application. When you're playing now with these kilns, this is where safety becomes pretty important, because talking about molten metal, you got to watch out for that, and this is where you have to start wearing a bodysuit and gloves and whole face protection, because if you have any droplets of water get in there, say you put in a wet piece of metal, that's calling for explosion. So this is high temperature stuff, a lot of stored energy in there. You want to be careful with what you're doing there, and if I were doing this, I'd get me a bodysuit, those bodysuits they use when working with hot metal, that reflective aluminized stuff, and that's something we would get into later on. How do you collect data on how much heat you have? Two simple ways to do that are by using infrared cameras. An infrared camera will let you know that you have a hot object. I like to show this. It's called Thermography. It's a thermographic camera that's actually open source and Arduino controlled. So take a look at that. You can take pictures, say of an object, and then you can take pictures with the underlying thermal image there. So there's a great open source project here that actually showcases that. You can take pictures and you see the image, like here, for example. Here's a superposed real image over the thermal image of whatever's going on in that picture. So that's an open source project. Otherwise, the simpler way to do that is with an infrared thermometer. If you have something that's very hot, you can get this on Amazon. That's a way to do that. On build techniques, just to wrap up on some of the considerations there, what we found, for example, in our build yesterday was it was actually very hard to get the nichrome wire fed through the sleeve, because the sleeve is so loose that the wire tends to poke out of it very, very easily. So we had to use like a guide header to go through it. But what I've seen people do, and that would be, let's go back to the first link we have there.
Did you do wire pulling?
Yeah.
Easy to feed wire, insulated 14 gauge or something through. Tape that to with electric tape to your nichrome and pull all that through. So you got
We tried that, but what happened with the sleeving was that the sleeve is so loose that things just very readily tend to go like right through it.
and then it all taped up. And
That's what we did, and at that point we fed it relatively effectively, but I think the findings from there is that not super practical because of the difficulty of that, unless you really refine it and have like the pooling wire thing. Let's go back to this thing, but on the wiki page under 120 volt heat bed, we have the other example here, so you can take a look at this 31 gauge wire, 19 feet, which is 90 watts in this particular example. But if you click on that link, what you'll see is the technique for if you don't want to have so much length, because that here is 19 feet. That's about 6 meters right there. It doesn't look like 6 meters, does it? Because it's not, because the wire inside is actually coiled around another piece of wire. So when you look at the detail here, that's the detail. How did I get that picture? That's what's actually going on there. So you take another piece of the sleeve and wrap the wire. A lot of wire wraps around it. You can hardly see this.
On the outside?
On the outside of it. So you shrink its diameter. Yeah. In other words, this structure will be now a factor of several times shorter than the initial wire. So this is what you want to do. Actually never got around to this, but I think from yesterday's experiments, we found that this is absolutely desirable. So you can have, we had 13 feet, about 4 meters length. Well, you have to put that into the second sleeve. So what you have there is the inner wire with the wire wrapped around it, and you send that through, and then you have full insulation around that. And once again, here you're crimping to whatever else you have. And here was a great application of one of these. This is like nice and tidied up, but this is how you do it. Okay, so that's the technique for building these things. You definitely want to be careful about having electrical shorts. So make sure that when you wind this through the sleeve, if you're winding a single, because you can do just a single wire. If you don't want to use the wrap on the inside, you can wrap one. But what we've seen yesterday is when we were poking the wire in, it tended to actually weave into the fiberglass sleeving, and that's a cause for a short, because it means it kind of went into the insulation, so it's insulated less. So you want to be careful about that aspect. Now, how much temperature do we get out of nichrome, this sleeving? That is pretty high temperature. In a 120 volt heat bed, let's go back to it. Let's look at the specs of that. What is the max temp that this sleeving can handle? It's on an order of 1,000 Fahrenheit. So in that case, what that means is that you're not using the sleeving if you're doing a furnace, because 1400 Celsius, the max temperature of Canthal wire, which is another form of nichrome, that would melt this fiberglass, because this is glass. So in that case, you don't use sleeving, you just attach the nichrome. And in that case, you might buy like coiled nichrome, where you're making your heater element out of that. So that's a little bit about build procedures. And going back to our wiki, let's go to the insulated heat bed and just wrap up with that maybe. Maybe I'll comment just a little bit more about the application to the most relevant thing right now, which is 3D printer filament maker, where you can either buy off-the-shelf heater bands or you can just use nichrome. Two options are equally valid and quite practical. With the nichrome route, you have the variability of controlling your parameters. You can design and build whatever size wattage, power, heater element that you want, whereas if you buy something off the shelf, it only has this one particular value. So here was the initial design of an insulated heated bed, and we actually moved on since this, but the diagram largely remains the same. So in the last version, actually 1904, we built a system where you simply use clamps around the metal plate. You've got the polyethermide surface at the top, which I showed. There's an 8-inch metal plate that's 1/8 inch or 3 millimeter. You got your fiberglass insulated nichrome heater. You have to put a thermistor in there so that you're measuring the temperature, and then you have the rock wool insulation. And in the last case, I thought about doing a 3D printed insulation holder, but no, don't do that here. You're talking about high temperatures, make that out of metal, so that you can also take this to higher temperatures. You might get away with it for maybe getting the bed to 60 C or 80, but this stuff is going to warp on you, and so use metal. You don't want to be mixing plastic when you have nichrome elements around, but that's the basic design. Right now, what we're doing is, and I'm going to maybe update that right here, the diagram of what we have done in the current version is we welded an elongated nut to the underside of the of the metal plate, and then we sent a bolt through it. There was a little hole. Oh, I did that wrong here. There's a bolt that goes through a hole underneath the bed and screws into the nut that's welded to the top plate. So that's how we're actually attaching the top plate. So you can open it, you can just unscrew that bolt and open the innards of that without having to use any kind of like clips or other fasteners on the metal plate itself. So right now, our metal plate is nice and clean, as you see here. No bolts or no clamps on that. You can see that those little marks there. That's the weld marks from the nut that we welded underneath. Last thing, so let's talk about the filament maker. We talked about filament extruders this morning. But for the filament maker, it is very convenient to make a nichrome heater like this, where you have a nichrome heater that's whatever power you want. And that does turn out to be lower cost, because nichrome wire, I mean, how much is it? You Google on Amazon. It's always talking about the cost engineering here. What's your cost for these heater elements? We said it was 30 cents a foot for the sleeving. And then for the actual nichrome wire, let's go to 26 gauge nichrome wire in the shopping list on page 2. There it is. You get 100 feet of it. Nichrome resistance wire, 26 gauge. And 26 gauge gets you just about the right properties for like a 500 watt heat bed. And I should emphasize that now, because we have 400 to 500 watts on the heat bed, our heat bed heats up faster than our extruder. So that's great. You can get printing right away. $7.29 for 100 feet of this. We're using about 13 feet of that, so about seven of these. So you're talking about $1 cost in nichrome wire per heated bed for 500 watts. That's great, because you actually cannot get a 500 watt heated bed off the shelf. I've looked for 8x8s, I couldn't find one. They have larger ones that are 500 watts, but 500 watts for a small heat bed, that's a lot. It's kind of getting industrial on you here. And then we're running at 120 volts, so we have a 120 volt heat bed with a ground fault circuit interrupter for a safety feature. But typically people run around 200 watts for the heat bed. We want to go fast so we can heat up fast if we've got production going on. And it's just pleasant to see it heat up so fast. The insulation, I actually took some data. I took the on-off duty cycles, basically how long is the heater on when you have an insulated bed versus the back being open, using our DIY heater. And I found that at 100 Celsius we're using 30% less energy, and at 177, so I actually took a look at the max of this, we're using 40% less energy to keep the bed hot. So that's great, because if you're running this machine, the 3D printer, 24/7 for a whole year, you're saving about $30 of electricity, so this pays for itself in less than a year. It's worthwhile doing an insulated bed. I don't think a lot of people do that. I don't think the energy consciousness is so much in there right now for this. But if you talk about industrial and you're doing large prints with much larger beds, yes, it absolutely makes sense. At that level, even 1 or 2% is something that a company would pay thousands of dollars for if they're doing large production. So, and we've got 30 to 40% efficiency increase by using the insulation. So, a good idea. In the extruder application, using the nichrome wire for heating is effective, because we can then create one heater element that is able to do whatever you need to do, as opposed to getting multiple bands, or we can devise other multiple small bands But primarily it's very low cost for high power heaters. Thank you. All right. So I think I'll wrap up with that. So the summary of this is nichrome wire is effective for a lot of applications. It's affordable. The techniques for building it are pretty much accessible. So if you want to build a fast heater bed that you don't have to wait 5 or 10 minutes for it to heat up, this is the way to go. So thank you. Any questions here?
If you were to make an oven with a microwire and that work as well?
An oven with
Like let's say
for
you're
nichrome,
doing-
with
yeah.
nichrome. So yeah, if you want to do a DIY oven or kiln for pottery, we talked about pottery and, for example, the paste extruder and making cookware, flameware out of clay, which I haven't seen anybody. I've seen pottery, but I haven't seen any flameware coming out anywhere yet. Flameware means stuff that you can put on a stove and it won't crack under a flame. Yes, those kinds of ovens are doable. If you want to talk about a cooking oven, but once again, electricity is not the most efficient way because you're using high-grade electricity to turn it into heat. Hopefully, well, if you have ample electricity, that makes sense. But otherwise, you might want to use flame.
But also for vacuum form.
Yeah, why not? The idea of nichrome is, compared to flame, is that you have fine control over it. You can connect that to some temperature thermistor or a thermocouple to get the temperature feedback, and you can use a controller to control it very finely. You perhaps may not be able to do that as well if you've got other heaters which are flame-based heaters. So the advantage is fine control in a tight space, like for example our extruder, where we've got a tiny little extruder kept at a very precise temperature to get uniform quality of prints. There you have to have a pretty tight control over the temperature, otherwise your filament would extrude faster or slower depending on how hot the extruder is. So definite applications to the bakery oven, one of the 50 machines of the Global Village instruction set. Any other questions? And let's look at the remote side. Any other questions on the remote side? So Herman says, I tried insulating a heated bed once by gluing a sheet of Bakelite underneath the aluminum heated bed. Did it work? What is Bakelite? Is that? Oh yeah. Did not work because of the difference of what? Yeah.
The rate at which, can you hear me there?
Yeah, we can hear you.
Just shortly. It did not work because obviously the two materials were did not deform evenly. So the aluminium will deform to a rate, and the bakelite will deform to another rate, and they will they bend in the middle pretty much.
I see. So you glued them together to get the thermal contact. Yeah, that's an issue when thermal expansion of different materials is an issue. So in our case, we're using wool, where that can move around a little bit. So the idea of having a bond between them is not an issue. Yeah, that's interesting. But yeah, I mean, the Bakelite, you would not be able to do 177C on that, which is what our bed is now rated for, which is perhaps one of the higher, not a lot of people print it at high temperature, but we want to do that for high temperature printing, for more exotic materials. All right, anything else on the side here? Justin?
Is it what? You say high-grade electricity. I don't quite understand.
Yeah. Okay. The concept of high-grade electricity is that unless it's solar powered, you're getting electricity by burning something, which is heat. You create high-grade electricity, a refined form of energy, and then you're converting electricity back into heat. So why not take that energy that you burn something in the first place, like coal or gas, use that in the first place. So you're not going through that change, because the process of producing electricity is at most like 40% or so in power plants. So you're creating high-grade energy, whereas you can be getting 100% of that energy from that flame itself. So you're wasting a lot of energy when you're converting some chemical fuels to electricity and then back into heat.
Okay. One other thing I just thought of. If you're generating electricity, say from some ocean like a windmill, then would it be more efficient to actually use that windmill to generate friction than it would be to generate electricity from the windmill and convert that back into heat?
The advantage of electricity is easily transportable.
Okay.
You have wires, copper wires, which are very, very low resistance, that you can take that energy and send it miles away. In fact, hundreds of miles away. For you to conduct heat, that's physically very difficult like that. So the idea of electricity is a very convenient form of energy that's usable. Now, if you have an application like a windmill, the thing about windmills is that you're going to have much varied power depending on how much wind there is. The power varies as wind speed to the cubed power, to the third power. So in that case, having resistive loads such as water heating does make a lot of sense, because then you can dump the excess power when you have a lot of electricity. And in a smart home, you'd be pretty much like switch everything to that windmill when there's high wind and turn off everything else, like if you have solar or anything else or whatever, send that. When you have excess electricity, it does make sense to use resistive loads, and in fact people dump these loads into a resistive heating. Now, there's a great advantage of using this kind of excess power for storage, like the idea I mentioned before about saturated water. Okay, an important concept here for storage. So say you've got excess heat, you can turn that into saturated water, which is a form of storage. So there's a page on the wiki called Saturated Water that people should be aware of, because I didn't really understand this until basically like a year or two ago. But saturated water is water at greater than 100 Celsius at pressure. And it's water, it's just plain water, no steam in there. Huh?
You call it superheated, right?
It's not superheated water.
It's naturally at that temperature?
Superheated water is when it, I believe, under no pressure, it doesn't evaporate.
I just thought it meant if it's heated higher than its phase change temperature,
Yeah.
and if it's still
I'm not sure about the terminology there. I'm a novice to this.
Superheated water is liquid water under pressure at temperatures between the usual boiling point 100 C and the critical temperature 374 C.
Okay.
There's also known as subcritical water or
So this is
hot water.
So it sounds like saturated water is superheated water. That's the first time I hear the two terms together. But saturated liquid, the definition of that is a liquid whose temperature and pressure are such that any decrease in pressure without a change in temperature causes it to boil. And that's the technical definition. What it means is you take a propane tank, 1,000-gallon propane tank, fill it with water, you heat it up with, say, your windmill or any solar heating to above 100, and the pressure of that will keep increasing, and stop the pressure increase at about 200 C. So don't continue, because 200 psi is what a pressure tank like the propane tank can easily handle. You can't keep going. You can't keep going way up, but it becomes impractical because of the vessels. Like they have to be stronger, and between 100 and 200, there's so much latent heat stored in there that when you put a little faucet on that and run it into a heat engine, such as a steam engine or a turbine, you're extracting that power at the standard heat engine efficiencies of 10, 20, or 30% efficient. What we're saying here is that without complex chemical storage, you can use water to trap large amounts of heat. Now the numbers there are actually pretty astounding. So if you get to some physical numeracy here, and I have those numbers there, we have that Bottom line. Where's the bottom line in there? So here we have bottom line is you're storing 20 to 30 kilowatt hours per meter cubed. Meter cubed is a meter cubed. 20 to 30 kilowatt hours at 200 psi. That's how much that hot water has in terms of energy. Now, you cannot get all of that out.
What's the efficiency? Like 20% maybe?
10, 20%.
Still enough for a day or two.
That's what we're saying. A propane tank, a 1,000-gallon propane tank, which I believe is like 4 cubic meters or so, several cubic meters. You're talking about water storing, you know how much a 20 to 30 kilowatt hour battery bank would be? Would be a lot. Here you're talking about water and propane tanks, or composite tanks of some sort. They have to withstand high temperature of 200 Celsius. It's about 200 Celsius and 200 psi. Those are the numbers. But read that page carefully, understand it, because I believe this is part of the world's energy future. There's a company right now, I visited the guide, and that's how I found about it. Where is that link there? Links. There should be a link here somewhere. Yeah, this is a calculator. You can find it online, how much energy that there is in that. There's a website. Let's see. Should be under the saturated water page. I don't see it. But if you talk about, you're off grid somewhere and you want to do this for real, there are practical steam engines that do that today. You can buy this quarter horsepower steam engine. Oh, let me share my screen again there.
The problem is that insulation, that's the problem.
Yeah, you have to put a big scumbag on it. Insulation, you got fiberglass insulation, you're going to put that in a big container, just pack it with insulation. But insulation is relatively cheap.
I mean, how you can hold it?
How would you heat that up?
How would you heat it up? Here's how. So let's take a look at some other links here, because I think this is very relevant. We start with a solar thermal concentrator for generating electricity initially with the Global Village construction set. This makes it completely feasible. So take a look at on the wiki. Are we showing that? Yeah, we're showing that.
Which under which heading?
On the wiki, would be under solar concentrator, but it's on my log under solar concentrator, DIY solar concentrator. So this is what OSE France has done right here. Yeah. Some people... Oh, where is that? Oh, here it is. Look at that. Read more about this. They did this solar concentrator. It looks like this. You can do it this way. Too expensive. Let's go to something better. I like this one. Right here. This is what you want to do. This is just, what is it, aluminized mylar film, 1-inch pipe. I mentioned the figure that a flat plate gets to 90 degrees Celsius by the law called, what is that, Boltzmann's law of radiation, sigma T to the fourth. That calculation gets you that when you have the sun at 1000 watts, a black surface will get to 90 degrees Celsius. Wow, that's already very close to boiling. All you need to do is increase that magnification 2 or 3 times, and you've got boiling water. So this is it.
Using reflecting?
using reflectors. So here you have an individual tube in each of these troughs, and this thing is cost, he uses Canadian dollars. Cost per 8-foot section is 150 Canadian dollars. So over $100. About $100.
Oh, sorry, 150 Canadian dollars. Sorry, less, like 120.
Yeah, a little less.
115.
Yeah, so there's some costs involved. Just one 8-foot section is like $100. Well, it's not necessarily that cheap. How do you get the cost down? I don't know. You're working with Mylar. You can potentially use maybe, I would say maybe like steel backing or aluminum backing. Steel is cheaper than aluminum, so maybe steel backing. And
So
then,
Mike can open it up for questions so we can grab a bite to eat.
yeah. But this, read about this. This is awesome. So that gets you, what I showed that concentrator there, that gets you to the saturated water. Water above 100 C. So you're pumping, you have to have a pump though that can pump up to 200 PSI. If it's a closed loop system, you don't need a pump, you just need a circulating pump. But yeah, so in this system you would connect this to your tank of hot water, and if that pump is at the pressure of a closed loop system, that pump doesn't have to have a lot of energy, so the energetics work out really well. But you can basically be tapping this kind of a system with like 50 watts of recirculating water power, hydronic pump, like in a water hydronics heating system for a house. You're circulating that, you're trapping your saturated water up to 200 C, and per cubic meter you've got 20 to 30 kilowatt hours of power that you can then use at an efficiency of about 10% to 20% with good steam engines. If you got an excellent steam engine, it will go up to 30%. But you can buy a 1/4 horsepower steam engine on eBay, actually, so let's show you that and then we'll wrap it up here. Here's a 1/4 horsepower steam engine on eBay. No, not bad. Let's go to eBay. There you go. These are model. What is that? That's a finished one. That's not what you want. You can get the kit for that for like not $2,000. That wouldn't be affordable. For like $100.
Not very efficient though, are they?
They're about 5% efficient. But believe it or not, that's what people had in their homes in the 1800s when steam came out. Before we had electricity, people would use steam power like this to generate electricity for their home, stuff like that. So an engine like this, that's 1/4 horsepower, live steam. So you can connect that. Now 1/4 horsepower is not a lot, but if you're efficient and you can run computers and lights on it, and a small fridge. I've got a super efficient fridge, so yeah. But you want to get to modern diversion technologies of that. And how do you do that? With the air-bearing lathe, you can have stainless steel, no lubrication, plain water, and you can have high precision, advanced modern steam engines. In fact, the modern steam engine, which is by Cyclone Power, Cyclone Power Technologies, cyclonepower.com, they make steam engines that are called modern steam engines, and they're more efficient than gasoline engines. So Google's cyclonepower.com, find out more about their steam engine. It's basically that. It's very high temperature and it's stainless steel, relatively relatively high precision. When we talked about air bearings, those are like pistons. Steam engines are reciprocating, so you can do that kind of stuff with the open source air bearing lathe. Okay, I'll quit at that. Any other questions?
Yeah, could you use hydraulic oil instead of water?
Can you use what?
Hydraulic oil instead of water.
Hydraulic oil has got a much different thermal cycle. You don't get those, like the boiling point is going to be much higher. And when you change phases, the releases of energy are going to be much lower. Water is an extremely powerful substance. So use that for oxyhydrogen cutting, use that for energy storage. We've got absolute abundance around us. I think it wins over lithium-ion batteries. it will get out there more as people wake up.
Is this water any particular, it has to be
No.
conditioned, just tap water?
You want it to be clean. So you might want to deionize it if you're talking about interacting with metals. Maybe, yeah.
So we're talking about getting the sun to heat the water, trap the heat energy of the sun, and then getting it close to steam, and then pushing the string to the steam engine, and then having a power generator
Yeah,
next to the steam engine that will generate electricity.
exactly.
Same concept as the power plants that coal with the sun.
Nuclear and
What about
coal power
heating?
plants do the same, except they use turbines, because above about 500 horsepower, turbines become more efficient than steam engines. At the small scale, below 500 horsepower, you only use steam engines. Above that, turbines.
That's his
What are the
screen.
ones that they have the
So he's showing stuff.
going out to a central
Wow.
training.
And then you sit there and watch that.
And all the time, actually.
Sorry, there's noise in the back. Sorry, sorry.
How about you, the ones we've seen?
Parabolic ones?
Parabolic,
Yeah.
where they have the mirrors and all shining into the dome on top and superheating that. Similar concept.
I would say that's doable too, as long as you can track that efficiently. So small Arduino controllers and motion systems like 3D printed motors, then you get the cost of that down to the cost of mirror, and yes, that becomes a
You track
cost
the
effective.
sun so you can keep
Yeah.
it focused.
Yeah. I'd say that's all she wrote.
Look up your, so to kind of get back to Aiden's comment, look up the specific heat of oil and like the energy, you can look up like
Yeah.
the energy and phase change. And then
Yep.
look up the specific heat of water and the energy for phase change in those two materials. And
Uh-huh.
you should be able to see, like what Marcin said, you should be able to see a pretty significant difference in, because your specific heat is directly related to the amount of energy that you can store in that medium.
Exactly.
I was only thinking in terms of those pumps. Like, area beer pumps.
Yeah, but then you have to do, well, you have hydronic water pumps. That's enough. If the whole system,
They can do that high pressure?
okay, so concept. When that pump is at 200 psi and the system is at 200 psi, the pumping is as if you were at no pressure, right?
It's not gonna go anywhere. You're just gonna.
It will be the equivalent of an unpressurized water system. So you gotta put energy like 50 watts, not like hundreds of watts or kilowatts. That's physics.
It's a relative pressure.
It's a relative pressure thing. If the system is closed, when you're trying to pump the entire system is 200 psi, you're using as much energy to pump that as if you were at standard temperature and pressure. Concept to understand. Because that means the pumping aspect of it is energy very manageable, energy-wise.
Okay, an analogy for it might be rolling a boulder uphill at 1,000 feet versus at sea level. It's still
Exactly.
got the same energy.
Good metaphor.
What about the water and what does that pump need to be made so it doesn't rust
Yeah.
the material?
If it's a closed loop system where at the end of the day the steam engine, you're condensing that water, then you put in some additives and rust proofing agents, or you go more advanced and make parts that do not rust, like ceramic parts, or maybe composite, plastic fiber composite parts that you can 3D print. So yes, you have to consider what kind of destruction is going to happen over time with water as the active medium. So you have to passivate it somehow.
Also, if you have like clean water, like Marcin was saying, you don't have to have perfectly clean water, but the cleaner the water is, the more like in like a power plant, I think they use like pure, like distilled water, as pure as they can get it, because that will corrode your pipes and cause additional issues, and it will also don't have to worsen any kind of pump or turbine you're using. You want the smallest number of particles you can get in those kinds of systems for longevity.
Yeah. And if you do the recirculating system, that means you have to have a condenser So a lot of times, like for example, steam locomotives, they do not recirculate their water, they just dump it out, so they have to get fueled up with water every so often. But you can do a closed loop system or an open loop system. In a closed loop system, you have to take care of the extra infrastructure for condensation, but then you keep the same water, you never have to add water outside of refilling a little bit. With the open system, you're constantly sending new water, new ability of that water to oxidize your system, because water has oxygen in it, so there's issues there.
Your system's also going to be much more predictable if you have
With closed loop.
clean water. I mean, it'll still be pretty close, but
Yeah, so some very important concepts in this lesson related to heater elements, and that gets us into saturated water and energy storage and extraction of that energy from that. Anything else? Okay, so I think let's wrap up here. Thank you very much for the remote audience. And everybody, replay this and understand the saturated water page is my hint for this lecture. I think it's very important and very practical, but I can tell you right now that nobody knows what the hell that is. So please learn it and change the world. I love how that happens.
so that's different than superheated water.
I'm not sure about that distinction. I think the saturated water may be superheated according to that definition, but I just haven't heard those two terms together.
Okay. You can superheat water in a microwave.
That's what I said, yeah.
Oh, did you say that? Okay, sorry.
Yeah.
Okay, so we'll
Put 3 minutes
stop the recording here. Thank you.
I mean, usually I hear saturated water in the context of like